Okay, then next up is our final talk before the panel. And this is about coverage guiding fuzzing of web applications, which actually probably leads on from the question we had just now. And Khaled, CTO of Code Intelligence, will be telling us about it. So Khaled is an expert when it comes to solving difficult and challenging technical problems. And as CTO of Code Intelligence, he drives the customer-oriented development of CI Fuzz testing platform. As a malware analyst, he's an expert in binary code analysis and has been working in reverse engineering and penetration testing for over 7 years. And now he's going to tell us a bit about how coverage-guided fuzzing can help test web applications. Khaled, the mic is yours.
Yeah, thank you, Matthew, for the introduction. Can you hear me well?
Yeah, I can hear you and see your slides. Everything's looking good.
Awesome. So, hello everyone, and welcome to my talk about coverage-guided fuzzing, or applying coverage-guided fuzzing for web application. And so at FuzzCon so far, we've seen really 3 great talks. So on the one hand, Simon mentioned why fuzzing web application is currently difficult. We've also seen Resla, and Fabian and Abhishek demonstrated that Jazzer is a very effective coverage-guided fuzzer for Java. And in this talk, I would like to shed some light on the special challenges that are related to applying code coverage coverage-guided fuzzing for web applications, and share a few insights on how we can address them. And here the focus will be on Java. And the end goal that we'd like to achieve is to make coverage-guided fuzzing usable for web apps, and as a result, enabling web developers also to benefit from this technology. So before getting started, let's discuss why web application security is crucial and why should we care about it. So as we heard, APIs are everywhere. So most critical code is in the web services. And more companies are moving towards a software as a service model to provide their services to the customers. So while this has advantages regarding deployment and updates, security flows in these scenarios have huge impact. So if you hack a client, or if you hack a single client, you only affect this client. But if you hack the web backend, basically you affected all clients, and this is really critical. And we also see that critical vulnerabilities such as SQL injection, cross-site scripting, and remote code executions are constantly found in these applications. And since the complexity of web applications is rapidly increasing, so is also increasing the need for an effective and automated test methods. So to give just some practical insights into the challenges of web applications, let's have a look at this small code snippet from web code. So web code is an intentionally insecure web application written in Java, and it's maintained by Opus, and it's designed to teach some security lessons. And so here we see the implementation of an endpoint that has an SQL injection vulnerability, and it's there because the SQL query is executed without any sanitizations. So here we see that it's a REST controller. We see the exact endpoint, and from the method signature, we see the parameters that are needed in the post requests. So this means that the request that we should send to this application should have a very specific structure. Otherwise, the login code will not be triggered. And obviously, a fuzzer or a dynamic analysis tool that just trying some random inputs will probably never reach this endpoint. Next, we see the call to the execute query method, where the SQL query is actually executed. And so even if we manage to achieve this, to reach this endpoint, how can we tell that executing this query may result in an SQL injection? So one approach that is widely used by DOS solutions. We have, as Simon said, we have some sort of built-in attack scenarios that attacks the application, tries to reason about the responses. However, since these tools don't look inside the application, this can be complicated by the fact that such calls might be, for example, protected in a try-catch block, and which means that this might prevent the analysis tool from seeing what's actually happening in the code, leading to either false positive or missing some code. And also we have program code is full of checks like this, meaning that interesting program behavior is only triggered when special constraints about the inputs or the requests are there. And so, for example, in this code snippet, the username of the request has to be Larry so that we can be able to execute the SQL statement. So just to summarize this, so in order for a fuzzer or a dynamic analysis tool to be able to trigger the SQL injection vulnerability, it needs to know exactly how the request should be structured. It needs to generate a request with a username Larry, and it needs to know that it has triggered an SQL injection vulnerability. Furthermore, web applications have like a more complex deployment. So here's an example of web code where it's a Docker compose file that starts multiple services. Of course, for real applications, this can get really more complicated. Applications consist of multiple microservices that are deployed, for example, in a cluster, which makes quite different from the traditional approach of fuzzing, where the fuzzer and the application under test run basically in the same process. And of course, here we don't want to only talk about problems, but so in the remainder of the talk, I will try to share some insights on how can we address these challenges so that we can benefit from the potential of coverage-guided fuzzing for testing web applications. So the first challenge is that we need structured inputs. And the good news about web applications is that there are only few standard protocols that we need to support. So as we saw in Marina's talks, for REST API, we can have use the corresponding Swagger or OpenAPI definition to know exactly how to talk with the application. And so what we need is that we need the fuzzing solution to be aware of the structure. And this is known in the community, in the fuzzy community, as structure-aware fuzzing. And this means that the fuzzer needs to understand the corresponding specification so that it generates meaningful requests and perform smart, high-level mutations that would still result in valid requests. And combining this with coverage feedback is very effective. And so let's see how this can be implemented, or how we can implement it in using Jezzer. So this shows the usual workflow of Jezzer. So Jezzer would just send requests to the applications, would execute the application, it gets feedback, and based on this feedback, it generates further inputs that maximize the code coverage. And for Jezzer, we have an interface that allow you to develop structure-aware fuzzing on top of it, meaning that you can enforce Jezzer or tell Jezzer how it should mutate or change the input so that they adhere to your grammar or specification. So for example, for REST APIs, we can, as Marina said, we can use the Swagger definition, the corresponding Swagger definition, and build on top of Jezzer the structure-aware fuzzer, meaning that a grammar, a mutator that would understands the grammar and would perform mutations that would respect this grammar. And this has the advantages that all the requests that the fuzzer would send will be valid and will be accepted by the application. And the nice side effect here is that we don't have to write fuzz tests. So have you seen in Fabian's or an Abhishek presentation, traditionally we need to write fuzz tests that would basically execute the method that you write to test. In this case, we can write or generate fuzzers without even having to write these fuzz tests. And even if for some frameworks like Spring Boot, for example, the API resolution can be done automatically. And this is, of course, you can use this interface to implement your own grammar and based on your scenario. And for that, I would encourage everybody to have a look at this in Jazzer. So let's move to the second challenge. So while maximizing code coverage and reaching deep code blocks is essential for fuzzing, the second ingredient to have an effective testing is to be able to check whether security violations actually happened as a result of executing a given request. And so traditional black box testing, as mentioned, they have some sort of built-in attack scenarios, and they analyze the responses that the application sends in order to see if any bugs have been triggered. And for example, Zap has a really great active scanners that detects a wide range of bugs. And to solve this, we have two solutions. So following the success of Google sanitizers, which basically use instrumentation to insert runtime checks into C and C++ to check for a wide range of vulnerability. And a similar approach for Java to handle these cases would be very effective. Meaning, because here we can see inside the application, so we can see how the code is executed, and based on that reason if a bug or a security violation happens. On the other hand, we can also integrate fuzzing with other Dust tools so that they can collaboratively work with each other. And let's see how the second approach would look like. So here, just a high-level overview how Dust solutions would work. Just the Dust tool, for example, Zap, would attack the application and checks if a security violation happened. And since that black box approaches, as Simon said, don't see into the code, it's hard they cannot tell if the different attack scenarios actually result in interesting or triggering new code areas or not. And so because they miss these insights. And this exactly where coverage-guided fuzzing shines. So one interesting approach would be to combine these two approaches in a way where we can utilize their distinguished strengths. So the core idea here is to use the coverage-guided fuzzer to explore the program and guide the other Dust tools. This means, for example, here when Jazzer finds an interesting input that results in new code coverage, this input is then forwarded to the Dust tool, for example, Zap, and then the Dust tool uses this input as a seed or as an example that it can attack. And this means that we will focus the Dust tool resources only on attacking requests that have unique or interesting code coverage that we know that they reach new code areas. And this would help these tools in the Dust tools, the black box tools, in solving these the difficult checks that they struggle with because of missing feedback. And in the same way, we can use Jazzer, we can use coverage-guided fuzzing to test if the inputs that are generated by the dust tool actually result in some new code coverage. So with this, we just close the loop and we use the fuzzer and the information that the coverage guided fuzzer has about the application to guide other dust tool. And this is proved to be very effective in practice. And the second solution is, and the really interesting approach would be to add runtime checks as part of the instrumentation. And these checks would just examine the state of the application or the program and decide whether a security violation was actually triggered. And to support this, Jazzer has an interface that allows you to define your own custom hooks. And this means that you can sort of register checks to be executed or to be performed at specific events during executions. For example, you can schedule checks to be performed before or after a certain method is called, or even replace a certain method call. And as an example, to show how we can detect that a potential SQL injection here happens is by using this hooking framework. Simply, we can add a check that would intercept those method calls that execute SQL queries. The check would simply execute the original method, or would call the original method in a try-catch block, and would check if an SQL exception is thrown as a result. So this would mean that the fuzzer was able to generate input that landed in an SQL query, causing a corresponding exception, which is a strong hint that an SQL exception happen or might happen. And so note that, and this method would even work if the original method call, like the execute query, happened in a try-catch or was protected in a try-catch block, because we intercepted this at the level of the function call. So since we have these deep insights into the code, we will see exactly what happens there, and we can perform really valuable checks. And so this, the hooking framework is part of Jazzer, and you can use it to implement your own checks. And the third challenge is that we have these various checks in the code, and we need to handle them automatically. And of course, it's infeasible for a black analysis, when using black analysis tool, to just come up with all use cases that are needed in this application under test. And it turned out that with coverage guided fuzzing, we already solved this problem, because as part of the feedback that the fuzzer would get, in the case of Jazzer, is all equals operations, all string compares or integer compares, and this would give the fuzzer valuable feedback that it can use to generate smart inputs. So, for example, one thing that Jazzer would see is that here in this example, the username was compared to Larry. So one of the things that they try is just use Larry as a username and see what happens. So this is very effective. And this is, and it's also crucial to keep track of all interesting inputs that the fuzzer, so that the fuzzer does not start from the crash, from scratch all the time. And this is, of course, by design in coverage guided fuzzing, where so all interesting inputs that the fuzzer gathered in previous runs that have a new code coverage would be stored in what we call a seed corpus. And this would make coverage guided fuzzing a perfect fit for CI integration, for continuous integration, meaning that for each run, the fuzzer would already start from the knowledge that it has gathered through all the fuzzing runs. And so before discussing the fourth challenge, let's hold on for a moment and have a look at how would the results of coverage-guided fuzzing in web code in this example would look like when we address the challenges we've seen so far. So what the net results would be like we have an effective testing and detailed bug reporting. And so here in this example, we see that we get the exact concrete input that the fuzzer used to trigger the SQL injection vulnerability. And we know the exact line of code that where this vulnerability was triggered. So the fuzzer was able to generate the request as expected by the endpoint. The feedback enabled it to use Larry as a username, and the runtime checks enabled fuzzer to verify that it actually triggered the vulnerability. And a very nice property of fuzzing, as we see here, is that it generates the concrete input for each bug it reports. And this means that you can start a debugging session by executing the application with the crashing input and use the stack trace provided by the fuzzer in the bug report to set up breakpoints. That makes it easier to navigate through the code. And these concrete examples help developers to better understand the reported bug and be able to fix it more easily as a result. So let's move to the fourth challenge here, which is for web applications, we usually have really complex setup and deployment. The application might consist of several microservices that communicate with each other over the network. And so this makes the traditional approach of fuzzing, where the fuzzer and the system under test have to run in the same process, hard to apply in this scenario. And of course, to enable developers to apply coverage-guided fuzzing in these complex scenarios without having to make substantial changes to the way they deploy their applications, we need a better approach. And let's see how this issue can be addressed. So here we see an example project consisting of several microservices that communicate with each other. And the Java virtual machine has a very powerful facility called the Java agent. And with Java agents, we can intercept applications at runtime, the applications that are running on the JVM at runtime, and modify their bytecode. And this is the method that we use in Jazzer to perform instrumentation by inserting these coverage markers into the JVM bytecode and also all the hooks that we defined. So if we go back to our example, we can simply attach a Java agent to the microservices that we would like to instrument and test. And the agent would then perform the instrumentation. And the instrumentation would then have to communicate the feedback back to the fuzzer, and this way over the network. And this way, this has the biggest advantage, of course, that you don't have to change the way you deploy your application in a testing environment. All that you need to make sure is that the fuzzer is reachable from the microservices, so the instrumentation can report the feedback. Here's some final thoughts. Of course, fuzzing is nice, but fuzzing is most effective when performed continuously as part of the development process. So this enables to find bugs and vulnerabilities early, and as a result, be able to fix them quickly. So, and ideally, as Abhishek mentioned, code should be fuzzed on each code change, or as a part, for example, for pull request, as we see here. And this would enable developers to get instant feedback whether their changes has introduced any bugs. And early feedback enables developers, of course, to quickly fix the bug, since the issues and all the details regarding the change are still fresh in their mind. And a recent empirical study by Marcel Blume of all bugs in VS Code revealed that, or shown that, 4 in every 5 reported bugs have been introduced by recent code changes. So more specifically, like 77% of the reported bugs were only regressions. And this shows that continuous fuzzing is essential when it's done continuously, and it needs to be integrated into continuous integration to make sure or to guarantee the security of the software. And as discussed, coverage-guided fuzzing fits perfectly since it keeps track of all interesting inputs that it generated over the time. And this continuous fuzzing would also enable you to get an overview about the evolution of the security of your application over time. So to conclude my talk, I hope I was able to show that instrumented fuzzing improves web testing immensely. It can achieve high code coverage with improved bug detections if we use them based on the instrumentation, and it has a perfect fit for CI/CD integration. So with that, it's a very effective method and to guarantee the security of web application. And so with that, I come to the end of my talk. And so thank you for listening, and I would be happy to take any questions.
Yeah, thank you, Khaled. That talk very nicely tied together all the other talks previously. And we've got a couple of questions. And the first one is from Taj, who says, fantastic session. Can we have some documentation to get started with Jazzer on web code applications?
So we will have a blog post in the ZAP blog post, ZAP blog. So we'll have some insights about how what we do in order to test web application with Jazzer. So stay tuned for that.
So follow Khaled on Twitter, Khaled Yakdan, and you'll definitely hear about where the documentation is going to be released. Then Mehdi asks, how does Jazzer compare to Restler?
So Jazzer, the main difference is that Jazzer is coverage guided, while Restler is black box. But as I show in the example where we can integrate Jazzer with other dynamic analysis tools such as Restler, so that Restler can benefit from the instrumentation capabilities of Jazzer.
And there's actually a follow-up question by Mehdi. He says, not sure if I understood correctly, but it looks like you'd have to instrument the backend code to be able to fuzz with Jazzer.
So of course, you have to instrument the code so that the fuzzer will get the coverage feedback, so that it knows I sent this request, and with that, I was able to reach these code areas. So for coverage-guided fuzzing, you have to instrument the code, yes.
If I understood that correctly, that's what's done by the Java agent, right?
Yeah, exactly. So in the context of web application, you just have to attach the agent to the service you'd like to test. This would automatically instrument it, and the instrumentation would then report the feedback back to the fuzzer.
So this happens automatically. It's not something you as a developer actually have to manually do.
So you can imagine it, you have your own deployment, as you don't have to change anything about that. The only thing that you have to do is just add or load this Java agent in the microservice. All the instrumentation and reporting would be done automatically, of course.
And I have a question which came through the private channel, and that's asking, can Jazzer look for SQL injection and XSS vulnerabilities?
Yeah, so Fabian showed how we found cross-site scripting, cross-site scripting vulnerability in the JSON sanitizer, and I showed an example of how we used instrumentation-based bug detectors to find SQL injections. Yeah, and the good thing about that is that you can, with instrumentation, can see exactly what happens in the code. So you can, even if, for example, the execute query statement is called in a try-catch block, you can still exactly see what's happening inside with the Hugging framework that Jazzer provides.
Okay, then looking at the time, we have one final question from Net Zero, who's asking if he was developing an Android app with Kotlin or Java, would he be able to use Jazzer for that?
So with Jazzer, you can of course instrument the code. It's not officially supported. We need some some modifications to support that, but it's not supported off the box, but it's not hard to do as well.
So keep tuned for that.
Of course.
Okay. We have one last question from Benaz. Do you have any plans to utilize the client-side analysis to enhance your tool? Because a large portion of the application logic resides on the client side in modern apps.
The question would be if it's, or how interesting is to test the client side, because usually when you test the backend, there you have the huge impact. Because if you attack a client, basically you just affect this one. But if you fuzz the backend, there you will have the most interesting vulnerabilities. But it wouldn't make a difference if it's a Java application where you have an API. You can either use Jazzer to test specific methods, or use the sort of the enhanced form to test your application, of course.
Okay. Well, then thank you very much, Khaled.